In the last 4 or 5 videos, we have been looking at the properties of images formed by convex and concave mirrors. Now the obvious question echoing in everyone's mind must be that in reality, where do we take advantage of these properties? Where do we use convex and concave mirrors? Let's study the uses of a concave mirror first. Have you seen solar heaters? Solar heaters are the devices that use the energy from the sun to heat something. It is the most common device which uses a concave mirror for its function. We already know that the rays of light coming from the object kept at infinity converge after reflecting from the surface of a concave mirror. Here, the sun is very far away and hence the rays of light coming from it are parallel near the Earth's surface. These parallel rays after reflection converge at a point called focus. This focus is a very hot location in space as all the reflected sun rays are concentrated at this point. If we bring a piece of paper at this point, it will quickly catch fire. Now we can use this property of concave mirrors to cook food or heat up liquids. All we need to do is place the container on this stand which is present at or near the focus. It will heat up after some time. You can even make a roti or a papad on this. Where else in the world do we use these types of mirrors? We can use concave mirrors to view the objects which are very far away from us. Yes, I am talking about the astronomical telescopes. How is a concave mirror used in a telescope? When the parallel rays of light from the distant star enter the telescope, they fall on the concave mirror which is placed on the opposite side. This concave mirror then converges all the light at a focal point. So the image of the star is formed at this point in space. The secondary mirror is then placed near this focal point. It's kept like this so that it can reflect the light upwards towards the eyepiece. And the eyepiece has a lens which then magnifies this image. This way we are able to see an enlarged image of a faraway object. This particular type of telescope is also called the Newtonian telescope as it was Isaac Newton who first came up with this concept. Which is the lens used here near the eyepiece? The lens used here is a convex lens or converging lens. Well, we haven't really studied about lenses yet. Don't worry, we will come to that very soon. First, let's continue to study the applications of curved mirrors. If you remember, in the previous videos, we talked about this mirror which can be found in bathrooms. Many men use it for shaving purposes and quite a few women use it for beautification. Yes, this is also a concave mirror. And it must be very obvious now as to why we use it here. Due to the enlarged image, it gives a better view of our face. One more place where concave mirrors are used is the headlights of automobiles. And why do we use headlights? Headlights help us to see things in front of us in dark or in dim light. And using the headlights, we would want to see the things which may be at a sufficiently large distance ahead of us. So how do we achieve that? Let me quickly review something about concave mirrors. We know that when the object is kept at the focal point, the light rays from the object after reflection travel parallel to each other for a long distance. So if we keep a light source, say a bulb, at or near the focal point of a concave mirror, then almost all the rays from the bulb after reflection will travel in one direction. If the same concept is used in the headlight of a car, it will give us the distant view of the road ahead. This solves our purpose of viewing cars or things which are at quite a distance away from us. However, in reality, we don't really want all the rays to be traveling parallel after reflection. That is, we also want some of the rays to travel a bit sideways. We not only want to see the road ahead, but also the things along the sides. This will help us see the vehicles coming from the other side of the road in opposite direction. So for that purpose, we use what we call as deflectors. They deflect some of the light rays by smaller degrees. Now that we're talking about a car, let's discuss its view mirror. What is the use of the side view mirror of a car? Is this also a concave mirror? Watch our next video to know more. In the previous video, I left you all with a question about the side view mirrors of a car. Is it a concave mirror or is it a convex mirror? Okay, let's look at the side view mirror of a car. To know whether it's a concave or a convex, we ask ourselves a simple question. What is the use of this mirror? This mirror helps us to see the vehicles that are behind us. So if it was a concave mirror, and if the vehicle behind is sufficiently close behind, then the image formed will be enlarged. By close, I mean it's between the center of the curvature and the pole of the mirror. And its size will keep on increasing as the vehicle comes closer. We don't really want such a big image, do we? Due to its bigger size, we are not able to judge the position or location of the vehicle behind. Also, it takes away all the space of the mirror. And because of this, we are unable to see any other vehicles or objects. So we cannot use a concave mirror as a side view mirror. So what about the convex mirrors? Yes, convex mirrors can be used as side view mirrors because convex mirrors never produce enlarged images. Images formed by convex mirrors are always diminished or smaller in size. And also the image formed by a convex mirror is always a virtual image. That is, it appears to be formed behind the mirror. What's the advantage here? As the image is smaller in size, only a small portion of the convex mirror is required to view the image. Hence, we are also able to see other vehicles and objects in the mirror. In fact, even faraway objects are visible as tiny objects. So a convex mirror is used as a side view mirror in automobiles. Where else are they used? It must be clear from this example that convex mirrors are used in a situation where we want the wider field of view of the surroundings. They are also used in shops, especially in shops or supermarkets which are huge with many commodities. Why are they used there? They are used there for security reasons. As they give a wider field of view, one is able to keep an eye on the happenings in a larger area of the shop. Another place where they're used is in ATMs. Again, for security reasons. It helps us to keep an eye on the happenings behind so that no one is sneaking up. So these were a few of the uses of the concave and the convex mirrors. In the next video, we will see one equation which is called the mirror equation. We will also derive that equation using simple mathematical techniques. This mirror helps us to. In this video, I want to derive the mirror equation. So what is a mirror equation? Some of you might know what it is, and some may be hearing it for the first time. Since it has the word mirror in it, let's first draw a mirror. Should we draw a concave mirror or a convex one? Well, the mirror equation works for both. But let's start with a concave mirror. You are already familiar with all these symbols. P is the pole, C is the center of curvature. It is the center of a sphere of which the reflecting surface is a part of. The midpoint of C and P is the principal focus F. And finally the line which joins all of them is the principal axis. Suppose that our object is kept behind C at a finite distance away from the mirror. We draw our usual diagram to get the image, which is of course a real image. So what is a mirror equation? Well, let me just write it down first. 1 over F is equal to 1 over U plus 1 over V. What do these three letters symbolize? They're nothing but distances between points. To understand better, let's draw a tangent at point P like this. In this equation, U is the distance between the object and the mirror. So this distance will be U. It is the distance between points A and P. Remember, the distance between two parallel lines will always be the same. So this distance is nothing but distance between points A and P. V is the distance between the image and the mirror. Let's name this point G. So V is nothing but the distance between points G and P. And F is the focal point, which is the distance between the principal focus and the pole. This distance is equal to F. Note that all the distances are measured from the pole of the mirror and not some other point on the mirror. So from the equation, you can see that it gives us the relation between the object's distance from the mirror, image's distance from the mirror, and the focal length. What if instead of this, I had placed an object somewhere else? It wouldn't change our formula. The equation does not depend on the object's position from the mirror. It is same for any position of the object. What if instead of concave mirror we had convex mirror? Again, it wouldn't change our formula. Yes, this formula is true for all types of spherical mirrors, convex as well as concave mirrors. Now the question is, how do we derive or prove this formula? There are many ways to derive the equation, but we will look at the easiest one. In order to derive this formula, we need to know only one thing, and that is the concept of similar triangles. You must have come across similar triangles many times in our math class. So let's review that first. In simple language, triangles are said to be similar if they have the same shape. For instance, these two triangles are similar since they have the same shape. This triangle is just a scaled down version of this. These two are also similar triangles. What's so special about similar triangles? When two triangles are similar, then the ratios of their corresponding sides are equal. For instance, here triangle ABC and triangle PQR are similar, so AB over PQ is equal to BC over QR is equal to AC over PR. And this fact is going to help us derive the mirror equation. The second thing about two similar triangles is that all the corresponding angles have the same measure. For example, here, angle A is equal to angle P, angle B is equal to angle Q, and angle C is equal to angle R. This also works in the reverse. That is, if for any two triangles, if we prove that their corresponding angles are equal, then they are similar triangles. This is called AAA test of similarity for proving two triangles similar. Similarly, if the ratios of their corresponding sides are equal, then the triangles are similar. Okay, let's go back to our figure for the mirror equation. Now from the top of the object, let me draw a line that meets the tangent at point B. This line is parallel to the principal axis. And from this point on the image, let me draw a parallel line again to the tangent at point D. Note that points B and D are not on the mirror. They're on this tangent which is drawn at point P. But actually, both the points are very close to each other in reality. This is because we have seen in our previous video that the aperture of the mirror that we are considering is much smaller than the radius of curvature. Because of the smaller aperture, these distances are very small, and so we can assume these 2 points to be on the tangent. So we can assume these 2 points to be 1 point and these 2 points to be 1 point. Now consider these two triangles. Are these two triangles similar? Let me first just draw them separately here. We see that angle OAF is equal to angle DPF. Why? They both measure 90 degrees. What about these two angles? Angle OFA and angle DFP? When two lines intersect, the vertically opposite angles are always equal. Hence, these two angles are equal too. What about the remaining angles? How do we show that they are also equal? With very basic logic, we know that if the two sets of corresponding angles are equal, then the third set has to be equal. Finally, we proved that triangles OAF and DPF are similar by the AA or AAA test of similarity. Now, because they're similar, we can say that OA over DP is equal to AF over PF is equal to OF over DF. We're not really interested in this ratio, so we will just remove it from here. Now, from this figure, can you tell me what AF and PF represent? PF is the focal length F, but what about AF? We know that AP is the object's distance from the mirror, which is U. But AP is equal to AF plus FP, and FP is the focal length F. So AF is nothing but U minus F. And what are OA and DP? They are the heights of the object and the image. Let's denote them with HO and HI. We're not done yet. This is not the formula that we're looking for. Let this be equation 1. Now consider triangles IGF and BPF. These two triangles are also similar again by the AAA test. I will leave this for you to verify. The ratios of their corresponding sides are equal. I will remove this ratio as it's not required. IG and BP are nothing but the heights of the image and the object. PF is the focal length f. So what's GF? GP is equal to GF plus FP. We know that FP is f. So what's GP? Yes, it's the image's distance from the mirror V. Therefore GF is V minus f. Let this be equation 2. Now let's invert equation 2 to get the third equation. We are almost there now. So we have these two equations now with us. They both have the same term on one side of equal to sign, so the other two sides will be equal. Cross multiplying and solving further will finally give us the required mirror formula. Finally, we have our mirror equation in front of us. It was fun to derive it, wasn't it? However, this is not the only way to derive the mirror equation. Now, if you remember, at the start of the video, I told you that this is a general equation. That is, this equation is valid for any position of the object and for any spherical mirror under consideration. But is it so? In order to use this equation, we must make sure that some rules are followed. We will see those rules in our next video. In the previous video, we derived the mirror equation. The mirror equation gives the relation between three things. And what are these three things? U is the object's distance from the mirror, V is the image's distance from the mirror, and F is the focal length, which is the distance between the pole and the principal focus. I also told you that the mirror equation does not depend on the position of the object. It is the same no matter where the object is kept. Also, it will be the same if instead of a concave mirror, we use some other mirror, say a plane or a convex mirror. As you can clearly see, all the three variables in the equation represent various distances. Now, how do we measure these distances? As I told you that this is a general formula. It means that it's valid for all types of spherical mirrors. But it's only valid for all spherical mirrors if certain rules are being followed. We can't use this formula if these rules are not followed. These rules are also referred to as sign conventions, called the new Cartesian sign convention. And what are those rules? Firstly, all the distances parallel to the principal axis should be measured from the pole of the mirror. All the distances U, V and F are measured from the pole of the mirror and not from any other part of the mirror. And the segment that is used to measure the distance should always be parallel to the principal axis. The second rule is that the object is always placed on the left of the mirror. The rays of light emerging from the object should always travel from left to right. The third rule is that all the distances measured to the right of the mirror are taken to be positive, and the distances measured to the left of the mirror are taken as negative. For instance, we know that when the object behind the center of curvature of a concave mirror, then the image is also formed on the same side. Both the object and the image are on the left of the mirror. Hence, both their distances from the pole are taken as negative. What about the focal length? Will it be positive or negative? The principal focus is also on the left. Hence, it will also be negative. And based on the second rule, we always keep object on the left of the mirror. Hence, this implies that the distance U will always be negative. What if instead of a concave mirror here, we take a convex mirror and keep that object at a finite distance to the left of it? In this case, we know that the image will be formed here. It is a virtual image. The object distance will always be negative. But since here the image is on the right, its distance V will be positive. What about the focal length? For a convex mirror, the principal focus lies to the right of the mirror. Hence, the focal length is also positive. Say the principal focus is 5 cm away from the mirror and the object is kept 15 cm away. What will be the values of U and F? We need to be careful with the signs. Since we know that U is negative, we will take U as negative 15 cm. And F is positive, so we will put its value in the formula as it is. Now we can use the formula to calculate V. If we solve this, we will get V as 3.75 centimeters. Note that the answer is positive value. So the virtual image is formed at a distance of 3.75 centimeters to the right of the mirror. Now what will happen if I don't follow sign conventions? What if I substitute positive values of U and F? In that case, I will get the image distance V as 7.50 centimeters. Which one is correct then? This one or this one? Well, obviously, this one is correct because all the sign conventions are being followed here. There's another way to tell that this is incorrect. We know from our previous videos that the maximum distance of the image from the convex mirror is the focal length. This means that the image of a convex mirror cannot be formed behind the principal focus. The maximum distance at which this image can be formed is focal length, and that is when the object is at infinity. So here, V cannot be 7.5 centimeters. And this value is greater than the focal length, which is 5 centimeters. Okay, this was all about the third rule. There is one final rule which is left. It says that all distances measured perpendicular to and above the principal axis are taken as positive, and distances measured perpendicular to and below the principal axis are taken as negative. Above, positive, and below, negative. So if we were to consider heights of the object and the image, both these distances from the axis are above the principal axis. Hence, they are taken as positive heights. Now, if this was a concave mirror and if the object was placed between C and F, then the object's height will be considered as positive, while its image's height will be considered negative as it's inverted. That's it. These were the 4 rules that we have to keep in mind. In order to use this mirror equation for any mirror, we must make sure that all these rules are being followed. In the next video, we will solve a few examples based on this equation.